Okay, just say it again. You could ignore me because you probably understand what I already said. You got an incline here, 5 inches higher at this end than this end. 48 inches, 5 inches. Okay. You got a mass M2 suspended over low friction pulley. We'll assume the friction is 0 everywhere. Not accurate, but we'll assume it. And got cart of mass M1, suspended mass M2, on down 2 over M1. And you really ought to be in the habit by now, but start by slopping down a picture like I did in lab. Okay. So, set that up. Okay. One thing I didn't mention that I interjected, it's kind of implicit, but we're assuming acceleration is 0 to the stationary moving at a constant velocity. Okay, so what we have is, first of all, mass M1. M1G. And we really want to do the entire body diagram. So among other things, we replace M1G, and I'm going to make that negative M1G times J. So we're very clear, and it's not times J. Okay, just negative M1G. And then we just cross out the M1G. It's M1G. Now, you got some angle here. What angle do we want to use? We could use the angle here. Or we could use the angle here. We could even use the angle here. We can choose our angle. Now, what you're more used to seeing probably is this angle here. And that's a good choice because it's the same as this angle here. Because if you start with a horizontal and vertical set of coordinate axes, then the weight is parallel to the y-axis. When you tilt this thing up by angle theta, the y-axis swings off by angle theta, and this is what you end up with. So this is then going to be M1G cosine theta J. It's going to be negative because it's in the negative J direction. So the M1G cosine theta times negative J, with of course a negative go. And it's intuitively opposite. That's negative. And this is going to be negative M1G sine theta times I. And of course, as usual, we have equilibrium in the, well, let's draw the force. First of all, we've got a normal force. Here. And then we have tension force back here. Because tension in the string is going to pull us, presumably, in the direction opposite. Well, the direction that would occur if the stretch string contracted. Okay, that's what tension's all about. Okay, so if the stretch string contracts, it's going to pull in this direction here, it's going to pull in this direction. All right, well, sum of all those forces is 0. I'm doing a good job with my space here. See if I can squeeze it all in here. The sum of the forces is zero. There's your basic principle, right? And I think that's on your sheet. Maybe it isn't. Probably wouldn't be a bad thing to add. Sum of forces is zero, the acceleration zero. Okay. So obviously some of the forces on this thing has to be zero, if the acceleration zero, because forces back, all that stuff. So some of the forces is zero, and it follows them that move myself room to write that whole thing out, but it's equal and opposite to this, which equals mg cosine theta times j. And since there's no friction, doesn't even matter what this is, but often there's friction, so we want to include it. And there is friction in the real thing we got there. There's a rolling friction that we will measure. Okay. Then really, I probably should have written this as F norm plus the negative mg cosine theta j equals zero. Therefore, this is equal to this and all that stuff. I'm going to write it out correctly here. Tension times tension plus the negative mg sine theta I, which I'll just remember for negative is zero. Attention to mg sine theta I. What's sine theta? Here's theta. Now you could find the angle theta by doing the arctangent of 5/48, and then find the sine of that, right? Or you could just say you wouldn't even do the arctangent. The sine is 5/48. Okay, it's 48 here, so the arctangent. Okay, the whole thing is you got a lot of trouble finding theta, so you can find sine theta, but use the inverse sine to find the sine. So you might as well just find the sine. Okay, so this equals (5/48) mg times the either. And that's M1G, so this should be M1 plus my subscript, something like there's M1, 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 and M1. Now what do we do? Come over here to M2. So now we've got M2. Negative M2G times the I vector and tension vector. Okay. Now, it's not the same tension vector we have here because tension acts in a different direction down here. There's our tension vector. And it's an equilibrium. And that's J not on. Attentions M2G high. Magnitude of attention. Is 548 mg. The magnitude of the tension here is M2G. Tension's equal here and here. So tension M2G is 548 of M1G. What's this tell you about M2 over M1? Or you divide both sides by G by M1G. So the ratio of the masses is 5 over 48. It's equal to sine theta. Okay. That's equal to sine theta. That's the analysis you need. And that's the depth of the analysis that you need to do more complicated or more complex problems. Now you see problems in the open math and in the text where this thing's on one ramp and this thing's on another ramp. It's like we've got two carts, maybe of equal mass, maybe unequal mass, on two ramps, maybe with equal angles, maybe not. You do the analysis instead of just remembering mg sine theta, which is dangerous because sometimes theta isn't even given with horizontal, okay? Which means it wouldn't be so there's the way you reason these things out. As I said, for the purposes of the major quiz, you're stuck in mg sine theta. It's not going to be great, but you probably at least get by, okay? Especially if you draw a free body diagram showing what you're thinking, because I'm more lenient grading the major quiz than the midterm that follows, okay? On the midterm, you're going to have to think a little more. You're going to have to do the complete analysis. Okay, so what I saw looked pretty good. I didn't see the details of the complete analysis, although some of you seem to be on track for that, just to give you time. Okay. Okay, again, wanting to talk about the same type of situation in terms of energy. So we do the usual free body diagram. Mass M, the remove displacement, delta X on the incline. We automatically start out with a free body diagram. There's our normal force. We don't really need to do anything with the normal force. We find that F net is negative mg sine theta times the I net. What's delta x? Really vector. Often we'll use a delta S instead of delta S. Delta S instead of a delta X. I'm pretty sure I said that wrong. Okay, we have delta X equals negative delta X times I. So what's the change in potential energy? Okay, so in free body diagram, we get the net force very easily, very quickly. Delta X is negative delta X times I, and the net force is negative mg sine theta times I. What's the change in potential energy? Okay, well, change in potential energy is equal to opposites. The work done under that conservative force. Okay. Now, can you tell me what I mean by conservative force? Okay, well, I asked for a definition of conservative force and got some reasonable attempts that finally came out with, well, it doesn't change. It's a force that doesn't change. Okay. If I toss this ball up and manage to catch it with this, it was a little weird because forget the braces there. Okay, it kind of bounced, but incredible reflexes managed to handle it, so nobody got hurt. Okay, anyhow, catch it with my fingers. Ball goes up, comes down. Okay. The force acting on the ball in the path up was equal to mgj. It's gravity down. When the ball came down, the force on the ball was mgj. Okay. Ideally, when you roll the ball, pull ball up the low friction incline, it should come back to its original point with the same velocity. That didn't happen. Okay, you made very accurate measurements and you are pretty well convinced that it comes back faster than it went up. Make sense? No, that didn't make sense. Went up faster than it came back. No, you did the numbers. Okay, watch me. Okay. Well, the nature of that force is gravitation. There's a gravitational nature to the force. This component of the gravitational force is the same whether they're going up or down. So it's conservative. Okay. So is this, but it doesn't do any work in this case. The thing that's not conservative is the friction. Okay, so the friction kind of sucks out some of the energy, kinetic energy you put into it. Okay, you started the ball, you put kinetic energy into it. By your non-conservative force, you throw a ball up and catch it. ball does equal and opposite work on your hand. Okay, that your hand doesn't spring down and spring back up. There's a little elasticity in your joint, in your muscles. Okay, the muscles and tendons stretch a little bit and they rebound a little bit. And that's an important factor in athletic training. Okay, so there's a little bit of conservative force there. I got to tell you something I did in the gym. I'm not going to tell you right now. It was just totally, I couldn't figure it out for months. Okay. So I got a tendon stretch and getting it's really good. A good workout, but it was really done the way I was thinking about it, in terms of this stuff. Okay. Certainly your muscles don't store up all the energy that compresses. Okay. If I lift a weight, pull back here, well, I get a little bit of elastic response. I've got to, it doesn't come automatically. I've got to put energy into it. I've got to burn the Cheerios in my bloodstream to create that energy, right? Because that's where all energy comes from, Cheerios. Okay, eat Cheerios in the morning, then have energy. Okay. And Cheerios come from the sun. They just stream out from the sun and we eat them. Okay. Maybe an oversimplification. But it's kind of a useful and somewhat humorous analogy because some of you are chuckling. Okay. Don't see any knee slapping going on, but some of you it look like I'm looking up. Okay. Okay, so you're okay. I'm getting around the bush a lot because there's a lot of bush to beat around here, but conservative forces. Oh, if and only if it's path independent. This force doesn't care whether you're going up the incline or down the incline, it's path independent. The force exerted on the ball when I throw it up, try to catch it, is path independent, okay? And if I throw the ball to you, force is still path independent. If you throw it to me along the same arc, you're going to have the same force everywhere. And of course, that was the good answer that I got about what's unique about a conservative force. Okay. It's constant. Path independent is a little better statement. It's a little more useful, but that was absolutely the right idea. Okay, so anyhow, change in potential energy. There's all my good chalk end up in there. Something isn't path independent. Okay, location my chalk. Well, think about that. Okay. It's equal to the negative of the work done by the conservative force. That's the equal and opposite part. Another way to say it's equal and opposite is say it's equal to the negative level. Okay, well, write down what's the work done by the conservative force now. It's good when you kind of multiplication you're doing with these vectors. Well, they're dot products, cross products, standard products, louder products, obnoxious products. Okay. So what do you get? That's a really good way to write it. With the vector nature. A lot of people are skipping it. We want to be sure, and that's okay, but we want to be sure. Understand how that works. That's good. Want to be careful of signs. Okay. You got a dot on that. That's good. You're thinking dot product because that's what it is. Okay. Okay, but what you're nobody's really totally written it down rigorously. And it's not hard to write this down rigorously. So okay, I recorded that, but unfortunately I didn't insult anybody by name. And then nobody deserves an insult on that one. Everybody did something pretty good. Okay. So the change of potential energy is equal and opposite to the work done by the conservative force. We have the conservative force here. Okay. This is conservative, as we discussed, it's path independent. And that's the simplest way to see that it's conservative. It's the same whether we're going up or down the incline. And net force isn't the same if there's friction. But right now we're saying no friction, so the net force is conservative. So, right, in this case, so this is conservative, so the work done by the conservative force, and if that is a vector, I should put an arrow over it. It's not F net times delta X, it's F net dot delta X, right? Negative mg sine theta I dot negative delta xi. I wrote it out really small. I might be able to write it a little bit. Equals negative mg sine theta delta x. Can you kind of make out what I'm writing there? See it okay? Okay. Should show up pretty well on the camera. Behaving itself, it usually does. Okay, so let's make that dot real big. Make that real big dot so we understand. We're doing a dot product. And of course, the details of the dot product are simply we factor out the I dot I, and we factor out the coefficients. We end up with an I dot I, which is 1. So that's very simple. In a minute, we're going to do it with the entire gravity vector. And we're going to see if we get the same result. Okay. The other thing, of course, about the change in potential energy is there are no non-conservative forces. And that force is conservative, so that the change in kinetic energy is equal and opposite to the change in potential energy. Okay. So now we can say that delta KE plus delta PE equals 0. So the delta KE equals the negative of delta PE equals negative of negative mg sine theta delta x. Which is mg sine theta delta x, which is exactly what you get if you use the equations of motion with this net force and this displacement. But we never had to touch the equations of motion. Got the energy picture. Well, delta x is delta xi. We could also write F net as minus mg sine theta I minus mg cosine theta j, couldn't we? Well, calculate this for us. So what do you get if you do F net dot delta x with these two? Start it up. Okay, so F net dot delta x is what? It's this, right? Well, I dot this with this. That gives me negative mg sine theta delta x times I dot I. And then minus mg cosine theta j times delta xi is negative mg sine theta cosine theta delta x. But it's times I dot j. What's I dot j? What's I dot I? And well, change my sine to cosine so life would be right. Well, I dot j is 0. I dot I is 1. So we end up with negative mg sine theta delta x, which is a whole lot like what we got over here. It's identical. That should make sense in terms of the idea that the dot product of two vectors is the component of one of the vector in the direction of the other, multiplied by that other. Okay, so your picture here, I really don't have room to write it on this board, so I can rearrange it a little bit. And I think this I've already done. Okay. Let's say that's negative m times the g vector, which is downward, okay? And then we have our delta x vector. Okay, I don't even put a coordinate system on this. I need to put a coordinate system on it to calculate the dot product. If I'm going to calculate it the way we did, really what I need is just this angle. Okay, and it doesn't matter which way the angle goes. In terms of our model here, this angle is 90 degrees minus theta. Well, that means if I take the component of my F net and my delta x, and really I should probably use delta s here because I don't have a coordinate system on this. And delta x kind of invokes a coordinate system, but it could be the same as the delta x there. It's going to work out the same. This net force has a component parallel to delta s and a component perpendicular. Of course, we calculated those in the context of the original problem. I'm going to call this force F net parallel, and I'm going to call this force F net perpendicular. Well, F net parallel magnitude of F net parallel is magnitude of F net times the cosine of 90 degrees minus theta. Well, cosine of 90 degrees minus theta is the sine of theta. With mg sine theta. film they're talking very consistently. The way that sort of gets grating after a while if you're not paying attention. Looks like good stuff. Okay, so if you're paying attention, it's probably really good. Okay, after that, delta S. Magnitude of F net, magnitude of delta S times cosine of theta, which is mg cosine of 90 degrees minus theta, sorry. It's cosine of the angle between, and of course that angle now is 90 degrees minus theta. So it's mg delta S sine theta. I never had to worry about whether it was a negative mg sine theta I, negative mg cosine theta j, or anything else. I've just got this picture of a net force in a delta S at some angle. I know the magnitudes of those forces. I know the angle. Calculate the work. Okay. And that calculation tells me that the only component of the net force that matters is the component in the direction of motion. That's important. It's important for a complete picture of work energy, kinetic energy, relationships, and so forth. Okay. Now we want to talk a little bit about what happens in terms of work energy if you've got friction. Okay, same picture, same free body diagram tells us that the gravitational force is the I guess I probably ought to indicate my X and Y axis here pretty well implicit. Okay, normal force is this. So the frictional force magnitude of the frictional force is equal to coefficient of friction, but I should have a K on it, times the magnitude of the normal force and everything that kind of bunched up. I just let me rewrite it. Now, why do I say magnitude? Well, I don't know the direction of the frictional force unless I know in what direction this thing's traveling. We'll assume V is not equal to 0. Okay, so what's your free body diagram look like? It's traveling up the incline. Well, we've seen it before. We've done it before. Right, look at this. Velocity could be Vx, which is now considered to be the magnitude of the X force. It's not a plus or minus thing, it's the magnitude. Okay. And I guess to mop it up a little bit, we'll put absolute value signs around. Okay. Bring an arrow over here. You know exactly what we mean by Vx, because sometimes when you're doing equations of motion and so forth, Vx could be a positive number or a negative number. Now we're in a vector situation, so that Vx is just the magnitude of the Vx vector. Okay. In this case, your free body diagram. Without labeling these things, because we know what they are. These are the components. So I guess maybe mg goes down here and then project it and then cross it out. Okay. So what's the direction of the frictional force in this case? Now Vxi, I is in this direction, so Vxi is in this direction. Friction has to be opposite. Okay. So the thing we want to see is the friction vector. That's the blue vector. In this case. Same diagram. Except with frictional force in this direction. Okay. Now it helps to remind yourself that Vxi is in the direction here, so here's Vxi, and here's negative Vx. It's not a force, it's a direction of motion, and the friction force is reaction to that, not a reaction to that, but it's the results of that. It's in the opposite direction to the relative motion of the two surfaces. Surfaces being with wheels, contact, well, rolling friction, and you got to worry about static friction, wheels aren't slipping and all that stuff. Bypassing all that, there's your picture. Okay, so now F net equals negative mg sine theta I minus mu k times mg cosine theta times I. I didn't write it over here, but the normal force in this case, and again, we've analyzed it, so I'm just going to write it down. Magnitude of your frictional force is mu k mg cosine theta. And this force is negative mu k times F naught, okay? So that goes this picture. This picture. Same, but now the frictional force is up the incline. So I don't know. The blue underline there's a change blue up there on frictional force. Make a trip delta x up and then delta x down. Work by the net force is I'm going to put a up subscript here, get a down subscript here. W net is okay. F net up is this. What's our displacement? We move distance, our displacement. We move distance delta x up the incline. Our displacement is then delta x times I. I'll put negative in the I there, but it's negative delta x I or x times negative I. Doesn't matter, okay? So quickly calculate these dot products and see what you get. Just going to give you a couple of minutes to do that, so slop it down there kind of quickly. And if you need to, you can copy it down before you leave. Okay, I'm just going to observe. If I dot I with this vector, I get a negative mg sine theta. Okay. So the part of this vector that dots with delta xi, this part of this vector is going to give me mg sine theta, negative mg sine theta times I, which is the work gravity does, well, as we move up the incline, because gravity is acting in the direction opposite our motion. If I dot this thing by negative I get a plus mg sine theta I. That cancels out the negative mg sine theta I have here. And if I didn't have friction, this would tell me that the thing comes down with the same velocity it had gone up, because the net work is zero. Okay, if it wasn't for friction, if mu k was zero, the dot product would give me zero, and the work done by the net force would be zero. Therefore, the change in kinetic energy would be zero, and the cart or pool ball or whatever would be coming down with the same speed that we gave it when we started. Okay, would arrive at the same point with the same speed. However, we have this and this. Now notice that these have different signs. So when I dot this with the I get a negative mg mu k mg cosine theta. Now this with the negative I get another negative mu k mg cosine theta. Okay. So change in kinetic energy is double this expression. Now it's telling us that the work done by friction as we go up and the work done by friction as we go down is the same. Okay, friction does negative work going up because if we're going up, friction's in this direction, opposite. And it does negative work coming down because coming down, now we're moving in this direction and frictional force is again in the opposite direction. I've alluded to that in the past, but this is a little more formal and a little more rigorous. And I'm going to ultimately want you to write up your results on that experiment in terms of this analysis. Okay? Okay, good.